Have you guys ever tried the bottle flip challenge? While it might seem like just a fun trick, there's actually some physics going on here. In this video, we'll explain how physics concepts play a part in a successful flip. When I launch the bottle, it follows a curved path through the air. This is a classic example of projectile motion under the influence of gravity after the bottle leaves my hand. The motion breaks down into two parts. Vertically, it accelerates downward at 9.8 meters per second squared, described by y equals v times t plus 1/2 at squared. Horizontally, it moves at a constant speed, x equals v times t. There's no propulsion once it's in the air, so the flight time and arc depend entirely on the initial launch angle and velocity. For a clean landing, the bottle needs enough hang time to complete a controlled rotation, but not so much that it over-rotates. That balance is where angular velocity comes in. Next is the spin. When you flick your wrist, you give the bottle angular velocity or how fast it rotates. Angular velocity is equal to delta theta over the delta times. Let's say the bottle is in the air for about 0.8 to 1 second. To make one full rotation, it needs an angular velocity of 360 degrees per second. If it spins too fast, it will rotate too much and miss the landing, just as in the video. And if it spins too slow, it will not rotate all the way. So the goal is to start with a spin around 360 to 400 degrees per second. That's fast enough to rotate once, but not so fast that it overdoes it. Then as the bottle flies, the water shifts inside and slows the spin just enough to help it land upright. Now, let's talk about moment of inertia, which tells us how much an object resists changes to its rotation. It's not just about how heavy the bottle is, but where the mass is located as it spins. Moment of inertia is equal to m times r squared. When the bottle is filled to around 1/3, the water is concentrated near the bottom. This keeps most of the mass close to the center, which means a lower moment of inertia and a faster spin. When it's filled to about 2/3, there's more water and it spreads out further as the bottle flips. This increases the moment of inertia and naturally slows down the spin. And because angular momentum is conserved, angular momentum is equal to moment of inertia times angular velocity. If the moment of inertia increases mid-air, the angular velocity decreases. That changes in spin rate helps the bottle stabilize in the air and improves the change of landing upright.
When you flip a bottle, the location of its center of mass plays a huge role in whether it lands upright or not. The center of mass is the average location of the bottle's weight. If it's high, the bottle becomes unstable and topples, but if it's low, closer to the base, it has a better chance of landing vertically. And this is where optimal fill level comes in. Too little water and the bottle spins wildly. Too much and the water doesn't move or shifts the weight too high. But at around 1/3 full, the center of mass is low and the water has room to redistribute downward during flight. This is the equation for a two-part system of the center of mass. B represents the bottle and W represents the water. So as the water slides down toward the bottom mid-air, the center of mass shifts downwards, making the bottle more stable as it lands. When you flip a bottle, you're applying torque, a force that causes rotation. Torque depends on how far from the axis of rotation you apply the force. This is the equation, where r is the distance from the axis and F is the force applied. When you flick the bottle with your hand, the torque causes it to spin in the air. But here's where it gets interesting. Because the water inside moves, the bottle's moment of inertia changes mid-air. It slowly spins slightly, helping it orient upright. Also, when the water moves slower, it reduces rotational instability by decreasing angular acceleration, since torque is equal to the moment of inertia times the angular acceleration. So lower moment of inertia or more distributed water mass makes angular acceleration more controlled. Let's move on to energy. When you flip the bottle, you give it kinetic energy and potential energy. This is the equation for gravitational potential energy, and it depends on how high it rises. This is the equation for rotational kinetic energy, and it depends on how fast it spins. Some of the energy is lost due to air resistance and internal motion of the water, and it's not a perfect system. But the key energy transfer is the energy you give the bottle gets split between translational and rotational. The bottle ends successfully when enough energy goes into lifting and rotating, but not so much that it flips wildly or tips over. And again, the water moving downward helps stabilize it mid-air and absorb some of the energy on impact. So, next time you land a perfect bottle flip, remember it's not luck, it's physics. Thanks for watching.